Conic section is the parabola. You looked at parabolas a lot back in 171. You had an entire section of the course for quadratic functions. Put it there. And so we'll start with just a review of quadratic functions from a 171 perspective. So back in 171, you could have seen or did maybe see functions that look kind of like this. F of x equals x minus 1 squared minus 4. So this is written in what's called vertex form. This is really similar to the format you'll be working with parabolas in this week in 172. But the standard form back then was a times x minus h squared plus k. Really, the only thing that came out of that from a characteristic perspective was that we could identify the vertex by using the ordered pair hk. We've talked about, or you've talked about in 172 so far, circles, ellipses, and hyperbolas up to this point, and there's a lengthy list of characteristics for the ellipses and hyperbolas. There's a pretty good list of characteristics for parabolas as well. But you've been looking at one of those for at least 2 semesters now, and that's the vertex. What we'll start with, though, is a review of how to create graphs of quadratic functions. So let's use the function, the one from above, the one there in black. The one thing we can identify is the vertex, and it's at the ordered pair 1, -4. So if we're going to create a graph, we'll start there. Oh, not so big. So the point 1, -4 is our vertex. And then back in 171, there are lots of different ways to get additional points on the graph, but one of the ways was to identify a pair of symmetric points. And so what that's getting at is the symmetric nature of a parabola. One of the other characteristics associated with a parabola is the axis of symmetry, and that's the vertical line passing through the vertex of the function, or of the graph. In our case, the axis of symmetry is the equation x equals 4. And so the symmetric nature, the symmetric points, what that comes from is saying, hey, if we travel from the vertex, if we go 4 units up and 3 units to the left, if that point is actually on the parabola, then its symmetric point is on the parabola as well. We would find that other point by traveling 4 units up and 4 units to the right. I think I said 4 up and 3 to the left, but it should be 4 to the left. So we should travel 4 to the right. And so to create the graph, and I'm going to undo all of this in a second because this is definitely not the graph we're making, but just kind of chatting about what it means to be symmetric points. A parabola, though, if you cut it in half at its axis of symmetry, the left half is a mirror image of the right half, and that's why it's called the axis of symmetry. And that's why we can use symmetric points to create graphs. If we find one point on the left side of the parabola and pair it up with its symmetric point on the right side, that's enough information to connect some dots and make the graph. So that's what we'll do here for this graph as well. How we can do that, all we need to do is pick an x value from anywhere on the left half of the parabola. 0 is a really cool one to pick. Let's use x equals 0 and calculate f of 0. So f of 0 is 0 minus 1 squared minus 4. That's 1 minus 4, which is -3. So if we travel 1 unit to the left of the vertex, to the x value of 0, just one spot to the left, we get an x value of we get a y value of -3. What that means for the symmetric nature of the parabola is if we travel 1 unit to the right of the vertex to an x value of 2, we're also going to be at a y value of -3. Those 2 points are symmetric points. Questions about how we found them, what it means to be symmetric points. So it's going way back to a 171 idea, not one that's probably come up too frequently or too recently. But why we can, yeah, go ahead, Booker.
Yeah, so why do we travel to the left first?
It doesn't matter. And for now, the reason we traveled to the left first is because I wanted to pick an x value of 0, and it happened to be to the left.
Okay, I see.
If the vertex had been over here at -5, I would have still picked 0 first. So in that case, we would have been traveling to the right. I just like to pick 0 because it's an easy calculation.
Okay.
But there's just no other reason. You could literally pick any point if you wanted to use -1 first or -2 first. Any of those are fine. So what we can do though, now that we have both of these points, or all 3 of these points, is to connect the dots to make our graph. And again, these aren't graphs that these are sketches. They're not perfect. They're certainly not perfect. I'm just using some characteristics and some information we've got to plot points and make a rough sketch of the graph. That's the focus of what we're doing. Questions about anything we did there? Okay. So next up in our rotation, or our plan for the day, is to practice completing the square. The feedback y'all gave me on that was exceptionally positive. So what we'll do is review completing the square. We'll do one question. If there's a request to do more, we can do more. But since the feedback was really good, we'll just practice one of those and keep going if that seems to be okay. What we would normally do is to complete the square for a series of functions and then graph them. So instead of completing the square first, we'll just practice graphing them instead. But let's do complete the square here. Since the feedback was so positive, I'm actually going to give you some time to practice completing the square here first, and then we'll review it together in just a second. So you're completing the square in order to write the function in vertex form, which looks like this. Okay, so let's see how that went. What we should do first is move the 2 from the right side to the left side. It's not part of completing the square, it's just kind of getting it out of the way is the point of that step. In order to complete the square, we need the coefficient on the squared term to be 1. Currently, it's a -3. So what we should do is factor out the -3 from the 2 x terms on the right side. That gives us -3 times x squared minus 8x. And then what we need to do is add a new term on the left side and a new term on the right side in the parentheses with the other x terms. What goes in that the blank on the right side is half of -8 squared. Whatever we add on the right side, we should also add to the left side. Just to point out on the right side, we're adding -3 times 16, which is actually -48. That means we should be adding -48 on the left side too. On the right side now, everything is, or what's over there is a perfect square. It factors into x minus 4 squared. On the left side, we can combine like terms to get -46. And then to place this in vertex form, we'll move the 46 back over to the right side. So here's the function in vertex form. We got there again by completing the square. But really, I mean, ultimately the point isn't to complete the square. The point is to have the function in vertex form so that we can graph it. Completing the square is just a kind of a tool that we use along the way to get to where we need to be. But what's really convenient is that the vertex is really quick to identify. It's at 446. So if we wanted to create the graph, and we do, we'd go 4 units to the right and 46 units up. That's way up there. I'm not gonna count off 46 marks. And then we would use, or could use, symmetric points to help us get enough information to create the graph. Again, I will calculate f of 0 only because that's an easy calculation to make by working with 0. We get -3 times -4 squared, that's 16, plus 46. -3 times 16 is -48. And -48 plus 46 is -2. What that means is that the point 0, -2 is on the graph. So here's that, 0, -2. Since parabolas are symmetric, knowing this point tells us another point on the graph as well. So the vertex is at an x value of 4. Let's use a different color. If we travel 4 units to the left of that, we get a y value of -2. What that means is if we travel 4 units to the right, the point that also has a y value of -2 is on the graph as well. And so then we can create the graph by connecting the dots through the vertex and through that pair of points. So the symmetric points were 0, 2, and, or sorry, 0, -2, and 8, -2. Questions about that graph? Or questions about completing the square? Okay. So again, since the feedback for completing the square was so positive, and there were no questions, let's spend a little bit of time just talking about the graphs. Then the feedback there was a little less confident, I guess I could say. So what I will do is give you I've written a new function on the screen. I will give you maybe a minute or two, to have a shot at creating the graph of this function by identifying the vertex. The axis of symmetry, just to practice doing that, that'll be something that comes up this week for 172 as well. And then a pair of symmetric points. You don't have to use 0. I will be using an x value of 0 for all of mine. You don't have to use that necessarily, but any pair of symmetric points will work. So see what you can do for those things. We'll chat about all of them in a minute or so and create the graph together. So the vertex is at the ordered pair -4, 1. The axis of symmetry, not a whole lot as far as the calculation, it's just the vertical line that passes through the vertex. In this case, its equation is x equals -4. But what we need is what we can use is a pair of symmetric points to calculate, to figure out the graph. So when I was saying I was going to use 0, I didn't realize we were going to be quite so far away, but we'll still use 0. So to calculate f of 0, that's 2 times 0 plus 4 squared plus 1. That's 2 times 16 plus 1, which is 33. So I don't have room to go up to 33. So let's just pretend that 33 is right here. 0, 33. Just above 10. We'll have to pretend a lot because that's really close to 10. But what that means is, so if we go 4 units to the right of the vertex, we are up at an x value of 33. The symmetric nature of parabola says if we go 4 units to the left, we're going to be up at an x value of 33 again. Those two ordered pairs, the one was 0, 33, the other one is -8, 33. Those are the symmetric points. We can use those to connect the dots in order to generate the graph. Questions about the graph? Okay. We'll try one more of those just because we're saving a little bit of time by not completing the square so many times. So let's try this, and I'll give you some time to try it on your own, and we'll check it together. But h of x equals -3 times x minus 1 squared plus 2. See if you can identify the vertex, axis of symmetry, and then a pair of symmetric points. So let's try this one. Oh my gosh, that's fine. All right, the vertex, it's at 1, 2. That's h with k. The axis of symmetry is a vertical line passing through the vertex. In this case, that's x equals 1. And then for symmetric points, again, I'm going to calculate f of 0. That's -3 times 0 minus 1 squared plus 2. That's -3 times 1 plus 2, which is -1. So 0, -1 is on the graph of the parabola. For us, for symmetric points, what that means is if since we traveled 1 unit to the left and have an associated x value of -1, 1 unit to the right of the vertex also has an associated y value of -1. So we can connect those dots to generate the graph. So the symmetric points, though, are 0, -1 with 2, -1. Questions about the graph for the characteristics? Okay. Then the next thing will kind of switch gears a little, pretty abruptly, I think. But we'll look at application questions. So you have time this week specifically dedicated to application questions for the conic sections. It could be the case that you've already looked at some application questions. I know in my class I try to incorporate some applications when we're talking about the conic sections for the first time around. And then on our applications day, we just look at more of them. So if if your class is kind of slim and you've already seen some of these applications, then that'll be good. But if you haven't seen any yet, you will certainly see some this week because that's when the specific time in the course is dedicated to applications. And so if you've heard me talk about applications in the past at any of the boot camps, my kind of thought process is that if you can take a word problem and turn it into a diagram, then you've eliminated the wordy nature of the problem. Folks can frequently not enjoy word problems, in fact, not even like word problems, but being able to eliminate the word component of that could be helpful if the words are in fact the issue. So what I always recommend is creating diagrams for problems. And so our point here isn't so much to answer the questions as it is to practice looking at practice creating the diagrams. The point of actually solving the problems comes up in 172 itself. Our point is to talk about things related to your topics for the week to get you in a really good position to actually answer the questions for the class. Anyway, sorry if you've heard me say all that before, but I put a screenshot of a problem in the chat. I'll give you a second to read over it, and then we'll just talk through creating the diagram. Okay, so what's going on here is that family has an ellipse-shaped pond in their yard, on their farm, I guess it says. We're told, so there's our ellipse, we're told that the pond has a maximum length of 58 feet. So from one side to the other, 58 feet. The maximum width is 42 feet. So from top, in our case, from top to bottom, that's 42 feet. In addition to this, the problem says assume that the center of the pond is at the origin. Meaning if we were to have kind of a graph behind this, a grid behind this, the vertex would be at the ordered pair 0, 0. So, the center would be at the ordered pair 0, 0. So, the question is to write the equation for the outer edge of the pond, of the ellipse. So we've incorporated everything from the question, from the problem. Questions for me about anything we've labeled. I'm going to talk a little bit more about this one just because this will be a good kind of review of the process. So for most of these application questions, your first task will be to come up with an equation for the conic section. In the case of this ellipse, the standard form for the equation is the standard form for the equation of ellipse is x minus h squared over a squared plus y minus k squared over b squared equals 1. To write the equation, we need to identify the numbers or the values that go in place of h, k, a, and b. H and k are really convenient here. H and k come from the center of the ellipse, but in our case, h and k are both 0. So we can put zeros in place of h and k. That gives us x squared and y squared in those numerators. Next, we will figure out a and b. A is the distance we should travel from the center to get to the outer edge of the ellipse horizontally. So from one side of the pond to the other was 58. Half of 58 is 29. And so 29 is what we would travel from the center to get to the outside edge. That means A is 29. And so in the equation, 29 squared is what we need. That's 841. We have a similar process for we have a similar process for getting the b value, except since b is underneath the y term, it comes from the distance we would travel vertically to get to the outside of the ellipse. Since the distance from the bottom to the top of the ellipse is 42, the distance from the center to the outside is 21. That tells us that b is equal to 21. And 21 squared is what goes in the equation. 21 squared is 441. So this is the equation of the pond. Questions about anything from that one? My point for today is to practice drawing the diagram, since this one was answering the question just involved a lot of things about the diagram and how characteristics come about. We actually solved this one. We came up with the equation. We won't do that for the next two. We have two more to look at. But questions about anything we did here? Sorry, I don't mean to keep coughing. I've not got COVID. I have allergies, and ever since we had the cold, rain and cold weather, the end of 10 or so days ago, and ever since then, the pollen has just been real bad, and I've been coughing a lot. Hopefully, with today's rain, that'll be better though. All right, so what I'm going to do, new question. I'm going to put a new question in the chat. It's a new screenshot. Okay, I'll give you a second to read over that, and then we'll talk through. Actually, we'll talk through this one since it's a parabola application. And you, chances are good you haven't looked at haven't seen the parabolas in class yet. So we'll talk through this one, and then we'll have one more. I'll give you some time to actually draw the next diagram when you're on. Okay, so for this one, we have a lamp, and it's has a parabolic reflector. So if you've ever looked, just to kind of talk about that for a second, because you'll see this type of question a lot with parabolas. I am going to try to find a picture from the inside of a flashlight. To kind of give an example of what I'm talking about. I guess that does a good enough job. So if you've ever looked inside of a flashlight in particular, it at least has an example of what this is talking about. So inside of a flashlight, you have the little bulb, but then it's got this reflective material, and the bulb's kind of just like inside, the bulb is surrounded by that reflective material, and that's what sends the light, projects the light outward from the flashlight. You know, if we didn't have that reflective stuff going on, you wouldn't have the nice beam of light coming out of the flashlight. If you've ever been outside and it's really dark and you just move your flashlight around, it shines a beam of light wherever you're pointing. If you were to just go outside and, with a light bulb, it wouldn't do that. It would illuminate kind of in a sphere around the bulb, but it wouldn't be this kind of projection of light, this beam of light coming out. That reflective material inside of the flashlight is what does this. And any sort of light that needs to be reflected for any number of reasons will have that reflective material in there. Frequently, they're shaped like parabolas. This one in my picture doesn't seem to be too parabolic, but parabolas are common shapes for things like this that need to be reflected, for lights that need to be reflected out for some reason. So that's what the question is talking about. And you'll see, and the only reason I'm talking so much about that is because there's a fair number of questions that have this similar kind of wording, and I just like to provide a context for that because it's frequently kind of a newer idea, I think. All right, anyway, we have a lamp with a parabolic reflector. And so I'm going to start with a parabola here. Not with arrows, but there's that. And we're told that the bulb for the light is placed at the focus of the parabola. So depending on where you're at in covering the material for the week, there's a couple of characteristics that come up in this question that that we haven't talked about today, but they will come up in your conversations for the week in 172. But just like the ellipse and the hyperbola, parabolas have a focus as well. And the focus is always somewhere inside of the parabola. So I'm not putting it at any specific spot, just somewhere inside the parabola. What we're told in the question is that the focal diameter is 8 centimeters. The focal diameter is the width of the parabola where the focus is located. So to get from one side of the parabola to the other, passing directly through the focus, that's the focal diameter. And in this case, it's 8 centimeters. And so the point would be to incorporate that information. I'll label the focus. The vertex is directly beside the focus. And so the point of the question is to take that information and come up with the equation for the parabola. After that, you can use it to answer any number of questions. But first and foremost, having the diagram and having it labeled correctly is a really big step towards figuring out the equation. We're not going to actually find the equation because you likely haven't covered parabolas yet unless you had class earlier today. But we do have the diagram and it is labeled. So questions for me about the diagram. Okay. So I'm going to put one more screenshot in the chat. It's a hyperbola question. Yeah. So I will give you some time, a couple of minutes, to read through that question and have a shot at creating its diagram. So what we've got here is a hyperbolic cooling tower. So that's I'm send a screenshot of that too, because I'm going to draw a diagram, but I'm not going to. The diagram certainly won't convey in the best light what's going on. So I'm going to send a screenshot of what the question is talking about. There's a picture. There's two hyperbolic towers. I don't know if they're cooling towers or not, but they probably are. But there's at least two towers shaped like hyperbolas, and the point is that things, whatever, typically they're involved in like some sort of manufacturing or production of maybe energy or something like that. But things get cooled off in here. And so we've got, what we're going to do is draw a hyperbolic cooling tower and label it with the information that's given here. So we're told that the base diameter is 100 meters. So the base of this thing is shaped like a circle, and the distance from one side of it to the other is 100 meters. We're told at its smallest diameter, which is directly beside the two vertices, in fact, and I'll go ahead and label the vertices. That at its smallest diameter is 48 meters. We're also told that the smallest diameter occurs 84 meters above the base, and that the entire tower is 120 meters tall. So there's everything we got, and let's see. The question is to determine the diameter at the top. Again, not our focus, but the point would be first to take this diagram and come up with an equation of the hyperbola, and then use that to answer whatever questions are asked. There could be part A, part B, part C, but generally you need to come up with the equation in order to answer anything else. So we have the diagram, we have it labeled. We can use that information to come up with the equation. Questions about anything we drew there, why it's labeled the way it's labeled, or about actually any of the three diagrams we drew. Okay. Then our last topic, your last topic for the week is graphs, polar equations of conic sections. So you looked at polar equations a couple weeks ago, or maybe 3 or 4 weeks ago. I think it was a topic on test number 3, near the very end of test 3. So we're going to revisit polar things. I'm just going to title this section Polar Things. We're going to revisit polar things one last time. It is actually the last topic for the class, I believe. And so just thinking back to the polar things, you looked at the kind of the core of that, the base of that was polar points. Polar points are written in the form of r theta, an r value with a theta value. Let's do that in a different color. So let's say we wanted to plot the point 3 pi over 4 written in polar coordinates. What we would do is identify the angle pi over 4. That one's here. Oops. And then we would travel in the direction, we would travel towards that angle, towards pi over 4, and go 3 rings from the origin. So hopefully that's seeming okay. It's coming back a little easier than maybe it came the first time around. What if we need to plot another point? Let's look at 4 with negative pi over 2. So what that means is we should first identify where the angle negative pi over 2 is. It's this one down here that I've highlighted in blue. Remember, negative angles, we start from the x-axis and travel clockwise. So just traveling 90 degrees clockwise from the positive x-axis. So here's the angle. We need to travel 4 rings. From the origin, we need to travel 4 rings towards that angle. So 1, 2, 3, 4. That point is there. Questions about either of those? Okay, so what if I'm going to write down one more. So what if we needed to plot the point -5 with pi? I'm going to give you just a second, not long, but give you some time to try plotting that point on your own. We'll talk about it in just a moment, and then we'll actually move on and look at some graphs, a couple of graphs. So we should first identify the angle pi. It's here, highlighting it in pink. But since our R value is negative, we don't travel towards the angle, we actually travel away from it. So I'm trying to highlight that. I'm trying to use a dash line to kind of blend it in. So I'm going to put the dash line a little bit above the x-axis just so you can see it a little better. But we should travel 5 rings away from the angle pi, which means we're actually traveling to the right. And the whole reason we're reviewing this is because we will use polar points to create graphs of polar equations, graphs of polar equations. And this week, the polar graphs will be conic sections. But questions about any of these polar points before we look at a graph? We'll look at 2 of them. Okay. So if you were here for the boot camp the day we talked about graphs of polar equations, one of the techniques I propose is using a table of values. It's not, using a table of values is always something you can do to create the graph of any equation you've got. For polar graphs in particular, that tends to be a really good approach. It may be not such a good approach if we're maybe looking at hyperbolas or hyperbolas or ellipses in rectangular coordinates. And we have all the characteristics we can identify and look at those that way. But for polar equations of conic sections, a table of values tends to be a good approach. So let's do that. Right. Again, if you were here the day we looked at polar graphs the first time, we always start with these 5x values, these 5 theta values. If we need to pick more, we can pick more, but these are always good points to start with. 0, pi over 2, pi, 3, pi over 2, and 2 pi. How this works, I'm going to give you some time to try this, but how it works is we take each of these theta values and plug them into the function, into the equation, keep mixing up 171 words at the moment. To take each of these theta values, plug them into the equation to calculate the corresponding R value. So at the end of this, we'll have 5 ordered pairs and we'll plot those. Since you get calculators for test 4, it's my recommendation to use a calculator. That'll, 1, speed things up, and 2, be pretty effective. You calculating the answer, you won't need to think of the unit circle and maybe swap some values around or something like that. So I do recommend a calculator. That's how I'm going to get the points in just a second. So give you some time to calculate these 5 R values, and then we'll check them together in a moment. So if you have a TI-36, these are really cool calculators to use for calculating things like this that have fractions inside of fractions. Because the calculator has a fraction button. I mean, I know lots of other calculators have fraction buttons now too, but the TI-36 are the ones that we recommend for the class, of course. Make sure you're in radian mode for these because the angles we're putting in are in radians. But I've just used the fraction button a couple of times, and I've entered into my calculator 1 over 1 minus 2/3 also as a fraction, and then sine 0. That gives me back an R value of 2. The really convenient thing about these, another really convenient thing about these calculators, and this is probably true for lots of other calculators too, is that you can scroll back up and select a previous entry you've made. That's really great for these because we're doing a lot of similar calculations. So I just scrolled back up. So after I got the answer of 2, I scrolled back up to the line where I entered the calculation, and I can push enter again to select that entry, and then I can just change the 0 to pi over 2, which is literally the only thing I'm changing, and then and push enter, and it gives me the next calculation of 6. I can scroll back up and repeat that process for the remaining angles we need. So 0, pi over 2, pi. At pi, we get a value of 2. 3 pi over 2 is next. We get back 6 over 5, which is 1.2. And then at 2 pi, we get back the same thing as 0, which is 2. So why we care about all of this is because our ultimate goal is to create a graph, and now we've got enough information to do that. We'll plot each of these points in polar coordinates and get the graph. So 0, 2, pi over 2, 6, that's up here, pi with 2, 3 pi over 2 at 1.2, that's a little bit past 1, and then 2 pi, we're back at 2. So connecting these dots, though, this is an ellipse, connecting the dots will generate the graph. Ugh, sorry, I'm trying to connect the dots in a good way. Hadn't done it yet. I missed it. I didn't connect, so we'll just make a bigger dot. There we go. There's our ellipse. At least a rough sketch of it. Questions about it? Oh, I didn't realize. Dang it. Didn't realize I covered up part of the equation. Okay, so I will scoot that one up. I'll leave that there and write the next equation we'll graph, and this will be our last one just so we can take some time for your questions. Try to save about 30 minutes for that. So r equals 3 over 4 plus 4 sine theta. So there's that one. I'll give you a couple of minutes to work on creating the table of values. Again, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those are our starting values. We'll use those to make the graph. Okay, so again, just calculating these numbers is the point. So I will use the fraction button in the TI-36. 3 over 4 plus 4 sine is 0. Whoops, not that button though. That gives us back 3/4, which is 0.75. Repeating that calculation, instead of at 0 now at pi over 2, we get 3 over 8, which is 0.375. Repeating it again for pi, we get 3/4, which is 0.75 again. If we calculate it at 3 pi over 2, we're going to actually get an error message. I'll talk about that in a second. If we calculate it at 2 pi, we're back at 3/4, which is, again, 0.75. So you're only going to get this error message for parabolas. We'll talk about why in just a second, but anytime you get this error message, that means the graph of the equation is a parabola. All right, let's plot them all. So 0, 3/4, pi over 2 with 0.375, pi again at 3/4 or 0.75. At 3 pi over 2, we don't get any point, we get the error message. And then at 2 pi, we're back at 0.75. So only with parabolas is this going to happen. But since we know it's a parabola, we can connect the dots like this. So it looks kind of similar to the ones we were looking at earlier where we have the vertex and then a pair of symmetric points. It's exactly what it is. It will always be a vertex and then a pair of symmetric points. But why don't we get one why don't we get a point to calculate at the angle 3 pi over 2? Well, 3 pi over 2 is this angle. Well, is this angle. And there's no point there, right? Since it's a parabola, the graph doesn't even exist in this space anyway. So that's the whole reason. Oh gosh, sorry. That's the whole reason why we get that error message. There's not a point down there, so certainly mathematically when the calculation is being made, there's not going to be a number that we get back. Questions about that one? Okay. Well, that covers the stuff we've got planned for the day. I didn't mean to go 4 minutes longer than usual. Just try to stop at 4. But I put the second survey link in the chat. If you would complete the second survey before you leave, That would be great. As always, I do appreciate you completing those. I know I ask you every week to do 2 of them, but I appreciate you hanging in there and doing them. So the rest of our time together, the remaining 25 minutes, is for questions that you got about anything you're working on, questions as always from today, or questions about anything else from the class. So I'm here now to answer any questions you've got. If you have no questions, or at whatever point you get ready to go, feel free to do that. But if you would, again, please complete the survey before you leave. So if you have questions, you can put them in the chat, or you can ask them out loud. Either way is fine with me. You're welcome. Thanks for coming, Jackson. You're welcome, Booker. Thanks for coming. What you doing?
Going to
Ariana, I know you're talking, but I can't understand what you're saying. The microphone's, it's pretty faint. And my volume is likely turned all the way up, yeah. If you're able, maybe you can type it, I guess. Oh, for the moment, I'm going to answer Alex's question. Can we go over how to create the equation from the... we can. That we can. It's a pretty wild ride, but we can certainly do it. I like the question a lot. Yeah, it's recorded. You'll have access to the recording through your chat. Since you were in the meeting, you can just once I end the recording, it'll some short number of minutes later, it'll automatically pop up in the chat history, in your chat history. So Alex, the hyperbola question is you're welcome. It's a horizontal hyperbola. We know that that's how the tower would be, is the branches would be opening to the left and right, which means the general equation is x minus h squared over a squared minus y minus k squared over b squared, and all that's equal to 1. And so actually what I'm going to do, if you'll hang on for just a second, is scoot all of this far enough away we have more room to write it. Okay, so here we go. So since it's a horizontal hyperbola, the general equation is x minus h squared over a squared, y minus k squared over b squared equals 1. All right. We need to fill in h, k, a, and b. Same thing we needed to do for the ellipse from the pond. Well, when you're completing these application questions, my recommendation is to make the center of the conic section at 0, 0, if you can do that. Like if you're given the discretion of where the center is placed, 100% of the time, I would put them at 0, 0. So let's do that. I'm writing the center. Let me do it here in purple. But here's the center of the ellipse in purple. That ordered pair is 0, 0. So we'll plug in 0, 0 for h and k. X squared over a squared, y squared over b squared is equal to 1. The value for a, just like the a value for the ellipse back with the pond, the a value is the distance we travel from the center to get to one of the vertices. Since the distance from one vertex to the other was 48, or is 48, from the center to a vertex is half of that, which is 24. So our A value is 24. 24 squared is 576. Said it's a water. I don't know if I've been thinking about that more since I said I didn't mean to paint a bad picture of the question. I think the question is great, but it's not as straightforward of a calculation as what we had for the ellipse, is what I mean. All right. To wrap up the equation, we need to figure out B. And we can't do that here because you don't have enough information to directly figure out B. We're going to have to do some other stuff. But that's why we have all of these other measurements, all these other dimensions for the hyperbola. So what we do need is an additional point on the graph of the hyperbola. There's only two other points we can find, and those are the two red ones down here at the bottom. So if we travel from the center, from the origin at 0, 0, if we travel, it's a little too far. If we travel over and down to get to that point, that red point down there, we can use that ordered pair to calculate B. Can you tell me the ordered pair for that point?
Would it be 50, 84, or 50 negative 84?
Yeah, 50 negative 84, 50 to the right because of the 100 at the bottom, and then 84 down because of the 84 we got on the left side. So why that helps us is we can plug in an x value of 50, a y value of negative 84, and now we have an equation where the only thing missing is B. So we could solve for B. Once we get that, we'll have enough, then we can create our equation. All right. So it's algebra from this point forward. I'm not gonna square these numbers. I'm just gonna do more rearranging for the moment. But what I'll do first is subtract 50 squared over 576 from both sides. We need to solve for b squared. So what I'm gonna do next, I guess we could have done it that way. What I'm gonna do next is multiply both sides by b squared. So that negative 84 squared is equal to 1 minus 50 squared over 576 squared, or sorry, over 576 times b squared. And then to solve for b, we'll divide by the stuff in the parentheses on the right side. So b squared is equal to negative 84 squared over 1 minus 50 squared over 576 squared. Or sorry, just over 576. I don't know why I keep squaring it. But then we can calculate that number. And that number is positive 2112 point. I'm just going to round it to 2 decimal places. 40. The thing is, yeah, it's not going to give me a fraction out of that. So just to point out, I'm not actually going to solve it for b. The equation we're trying to create has b squared in it, and b squared is what we already have, so there's no reason to square root to get b, just to square it back to get b squared. So our equation, though, is x squared over 576 minus y squared over 2112.4 equals 1.
Thank you for that. I appreciate it.
Yeah, of course. What other questions can I answer?
That's it. That's the only thing that I was kind of confused on. But
Oh.
going through it, thank you. I appreciate it. Because I was trying to work on it on my own, but I just like missed that step of like the 50 negative 84, like finding that point. But I see that now. It makes a lot of sense.
Yeah, there's a couple. There's some parabola question. There's some parabola questions like that. Not so you have an applications an assignment of applications in the lab manual. But for the parabolas questions, this wasn't an application, but there was a couple of questions where you actually needed to use an additional point on the parabola to get its equation. Just not an application, just a regular kind of generic parabola. But if you're ever stuck with finding an equation, if you don't have enough information to directly find HK, A, and B, like we had for the ellipse, see if you can identify another point on the conic section, and maybe that'll help, like we did here.
Okay. Thank you. Have a good day.
You too.